Welcome to this video session. My name is Samuel Dominic Chukwu Emeka, aka Sam Dom for Peace. In this video session, we shall discuss an important topic in discrete mathematics. And that topic is mathematical induction. This will be part one of the video because there are so many questions to solve. So this will just be part one of the video playlist. What do we mean by mathematical induction? So when this topic comes into question, you know, when you think about mathematical induction, then some people might think about, okay, induction first, then mathematical induction. Some people who have taken a philosophy, would probably have done reasoning if you've taken philosophy. And then, you know, you have generally two types of reasoning. You have inductive reasoning and deductive reasoning. Okay, induction and deduction. When you have something like all men are mortal, and then you say John is a man, therefore John is mortal. And then you come again here, you have John is mortal, John is a man, therefore all men are mortal. So if you have taken philosophy as a course, you probably have come across reasoning, this kind of reasoning. This one here, you have two premises and a conclusion. Here also you have two premises and a conclusion. Now in this kind of reasoning, you go from a general premise to a specific conclusion. Okay, and that is deduction, or you can say deductive reasoning, whereby you go from a general premise to a specific conclusion. General premises, in this case we have two premises and a conclusion. So you go from general premises to a specific conclusion. That is deduction or deductive reasoning. Then in this case, you go from specific premises to a general conclusion. That is induction or inductive reasoning. Inductive reasoning. Okay, so why am I explaining this? I am explaining this for those of you that have done philosophy before viewing this video, because I don't want you to confuse this topic with this here. Mathematical induction, you would think, okay, it's gonna be inductive reasoning, okay, but it is not so. Actually, mathematical induction is a form of deductive reasoning. So why wouldn't you call it mathematical deduction? Okay. Why would you call it mathematical induction? Okay, so see what happens. This is philosophy. Okay. And you know, with mathematics and philosophy is all tied together. But look at how mathematical induction works. Okay. So this applies to, first of all, well-ordered sets. anything that is well-ordered sets, such as your sets of natural numbers, okay, your set of positive integers. So any well-ordered sets, we apply mathematical induction to prove anything any formula you find about a well-ordered set, any formula at all, or any statement that you find about a well-ordered set, you can use mathematical induction to prove it. And how it works is, you first of all test it, okay? Test it, have an initial step. Test it for this first case. First case in that set. The first person in that set. Okay, does this formula or does this statement work for that first person? If it works, okay. Test it for some n equal to some people. Does it work? Okay. Well, if it works for the first person, and then assume it works for some of the people in that set, well, anybody that comes in, it should work for the person. Okay. That is the idea. That is the idea. So with mathematical induction, and I'm not going to go into, okay, you might ask me, okay, why don't we call it mathematical deduction, since it is deductive reasoning rather than inductive reasoning? Okay, I'm not going to go into that. If you really look at if we really do many problems in mathematical induction, if you really look at the real sense of it, you would find out that it's actually deductive reasoning. Now, you might say, okay, well, we first of all tested it for one person. Okay, you test it for one person. Oh, it works for this one person. Well, test it for some, then assume it works for some people. Then therefore it works for any other person that comes in. Okay, so let's just get back on track. So when we talk about mathematical induction, please don't confuse it with inductive reasoning. It is not inductive reasoning. Okay? It uses some form of induction, but it is not inductive reasoning. Okay? It is actually deductive reasoning. And how does mathematical induction work? Mathematical induction is a method. It's a technique. Okay? It is a method or a technique used to prove a formula or a statement. Okay? If you have any formula or a statement about any well-ordered set, you could use mathematical induction to prove that formula or statement. So mathematical induction is a method, or you can say it is a technique that is used to prove a formula or a mathematical statement of any well-ordered set. Okay? It is used to prove formulas that applies to well-ordered sets. That is what we mean by mathematical induction. How does it work? So you have a statement about a well-ordered set, or a formula about a well-ordered set. Hey, for so set of positive integers, this should work. Okay, let's see whether it's true. We have the first step, initial step. Get the first guy in that set. Get the first person in that set. Let's test this formula. Oh, it works for the first person in that set. Then we now assume that it should work for some other people in that set. And then we now say, okay, what if another person comes in? Let's see whether it works for that person too. Okay? If another person joins in, after you've assumed that it works for some people, then another person now comes in, okay, does it work for those people and that person that came in? Okay? Let's solve questions. By the time you solve questions, you would have a good understanding about it. Number one question. Prove that the formula works for a set of positive integers. A set of positive integers is a well-ordered set. Okay, so we are going to solve at least 3 questions in this video. So let's start with simple ones. So here, prove that the formula works for the set of positive integers. Okay, for the set of positive integers. You can also say prove by mathematical induction. Some people will say prove by mathematical induction that this formula is valid for the set of positive integers. So number one, you have 2 plus 6 plus 10 plus up to plus, this means continuous. Ellipsis, this is ellipsis. These 3 dots, you have 3 dots. It means ellipsis. These 3 dots here. Ellipsis, we call it ellipsis. It means continuous. Plus 4n minus 2 equal to 2n squared. Alright. So, we have the first step, initial step. Initial step, let's say that let's test this formula for the first guy in that set. Okay, let's test it for the first guy in that step. This initial step, some textbooks will call it basis. Basis step. Some textbooks will call it basis step. But I'll be calling it initial step. Okay? I'll be calling it initial step. So now we now say, okay, on the left hand side, because I'm doing this is left hand side and this is right hand side, I'll be using it a lot. So you know what, initial step, let's test it for the first guy in that step. N equal to 1. Okay, the first guy in that step. So my left hand side and my right hand side. So my left hand side, n equal to 1 is 2. Is 2. That's the first guy in that set. Is 2. Okay, the formula that we want to prove, this is the formula we want to prove. So we now put 2 times, in this case, this is, my n equal to 1 is just this first guy here. But then, in this case, this means 2 times 1 squared, which is 2 times 1, which is equal to 2. You see that? So it works for this step, the initial step. Now, for me, this is for me. This is for me. It's not for textbooks, okay? For me, when I solve questions for mathematical induction, I don't just do initial step. Initial step means test it for the first guy in that set. Okay, first guy in that set. Make sure that the left hand side and the right hand side satisfies that condition. In this case, is equal to. You must not always see equal to. Sometimes you see greater than, sometimes you see less than. Okay, you might see inequality. You must not always see an equation. So, but whatever you see, make sure that the left hand side and the right hand side satisfies that condition for the first person in that set. Okay. Now just for me, I like to test it for other steps. Okay. I like to test it for at least second and third step. For me, this is just for me. For me. Okay. I like to test it for second and third step. So I have, for my n equal to 2, my left hand side and right hand side. And no professors will not penalize you if you do it for at least second case and third case. Okay. For me, this is the way I solve it. After testing it for this initial step, I try to do it for second. Left hand side will be 2 plus 6, and that gives us 8. Okay? Right hand side is 2 times 2 squared, because this is the right hand side. This is the right hand side here. Right hand side. Okay? 2 times 2 squared, and that is 2 times 4, and that is 8. It works for the second. Okay? And I still go ahead and do it for n equal to 3. On the left hand side, you pull 3 terms, 2 plus 6 plus 10. 2 plus 6 is 8. 8 plus 10 is 18. Is 18. Then the right hand side, you have 2 times 3 squared. Okay? Because left hand side, you don't have n. Like the first guy is n equal to 1, second guy is n equal, first and second guy, you see this is addition. That's why you have to add. Okay? So right hand side, 2 times 3 squared, this is 2 times 9, and that is 18. So this is just for me. Now, and you must not do this, you must not. But that is the way I prefer to do it. Any mathematical induction that I do, I try to test it for at least 3 cases. Okay, that's what I do. If it works, then we now have what we call the induction hypothesis. Induction hypothesis. Okay. This is the next step you need. Some textbooks will call it inductive hypothesis. So we now assume n equal to k. Initial step is n equal to 1. Inductive hypothesis or induction hypothesis. You now say, let's assume n equal to k for some form, for some members of the set. Okay? First, initial step is first person in the set. Then assume that this works for some k, for some members of the set. So in this case, we just write everything, but we just, wherever we see n, we put k. Okay? So we have 2 plus 6 plus 10 plus, continue, plus 4k minus 2 equal to 2k squared. So you just hypothesize, form a hypothesis that this works for some k, for some members of the set. Okay? Then, the now interesting one is now the induction step. Induction step. Induction step. So, in this case, we now say, okay, let n be now k plus 1. So, if it works, and this is the way we are trying to reason, it works for the first guy, first person in the set. The formula works for the first person in the set. Okay, so we assume that it works for some people, for some members of the set. Then we now say, okay, if any other person is joining, it should also work for that person. So you kind of see how the reasoning works. You kind of see how the reasoning works. Okay, assume n is equal to k plus 1. So what we're going to do now is, we are going to now get this k, because after k, we now have k plus 1. So if another person comes into that set, it should work for the person. And how do we test this? So on the left hand side, we will have the k. We've already have n equal to k. Then we add the next guy. Okay, the next guy, we add the person, the next guy on the left hand side. Then we now use that formula also. We now substitute for n equal to k on the right hand side and see whether the left hand side will give us the right hand side. We do some algebra. If it gives us the same thing, then we prove it. So we now have left hand. I'm going to start with left hand side. So in this case, we have 2 plus 6 plus 10 plus 4k minus 2 plus, this is our n equal to k, okay? Plus the guy that is coming will be 4 times k plus 1 minus 2. Okay? So look at what I've done. This left hand side. So we have this here. I'm going to use this another color, chalk. This is our k. N equal to k. Right? We assume that it works for n equal to k. Now, if somebody else is joining them, okay, this is our k plus 1, k plus 1, k plus 1 term. Somebody else is now coming in. Okay? That is what we just did here. For the left hand side, somebody else is now joining them. So we will come and solve this. Okay, we'll come and solve this, and then we will also now do for the right hand side and see if we get the same thing, then we are good. Okay, so I'm going to erase this second column because, like I said, it's just for me. You really don't need to do this one. But you will not get penalized if you do it. I just like doing it. Okay? So, now, in proof, we're asked to prove something. Okay? We're not asked to disprove. We're asked to prove it. So for them to ask us to prove it, that means it works. So what I do is, I write my left hand side. Then I now do my right hand side and see what do I expect to get. On the right hand side, I do it, find out, and then I now work on my left hand side and make sure that I get that. Okay? So right hand side, okay, and let me repeat. When you do the induction step, we assume n equal to k plus 1. So you added somebody there. You find the left hand side. So you have the k terms and the k plus 1. Okay? The next person joining them. Then I now say, okay, I now come, okay, I now come and say, let me see what I will get on the right hand side. Let me see what I will get on the right hand side. If I now see what I will get on the right hand side, I get it. Then I now solve the left hand side to make sure that I get that. Remember, you are asked to prove it. So for you to have been asked to prove it means that it is correct. You just have to prove it. So on the right hand side now, I have my 2k squared, but in this case, n to be k plus 1. So I will have 2k plus 1 all squared. This is what I have on the right hand side. Okay? For n equal to k plus 1, this will now be 2k plus 1 all squared. So this is what I expect to get. Now let me now work on the left hand side to make sure that I get this. So this here, k, gives me 2k squared, okay, plus, I now have here, let me write this. So from here you have 2k squared, because this n equal to k gives you 2k squared. Now plus this here, this will be 4k, actually this is, I didn't write, well, this 4 should be here actually. This 4 should be here. Okay? This 4 will have to be here. That is the way it should be. Okay? The 4, because this is 4k. Anywhere you see k, you now put k plus 1. So this is 4 parenthesis k plus 1 minus 2. So that is the way it should be. So this will be 4k plus 4 minus 2. This is my left hand side. Okay? This is my left hand side. So let me come and make sure that I finish my left hand side and see that I got it right. So we have 2k squared plus 4k. 4 minus 2 is plus 2. Right? Factor by GCF. You have 2k squared plus 2k plus 1. Okay? And this will give you 2k plus 1 all squared. Your left hand side. And that means you've proved it. And that means you've proved it. Okay? Don't you worry. Let's solve more questions and you will understand it. Okay? Let's do number 2. Let's solve more questions and then you understand it. Let's start with question. The next one is question 2. We have 4 plus 9 plus 14 plus, I'm trying to do as, you know, I'm trying to start with the simplest and then, you know, this is 5n minus 1 to give us n over 2 times 5n plus 3. Okay, so we are going to still use the same method. Now remember, questions 1 and question 2 are sums, that if you keep adding them, it gives you that. Okay, so first step is initial step. Initial step, n equal to the first guy there. Let's see here, left hand side, right hand side. So left hand side is 4, first guy. Okay, right hand side will be 1 over 2 times 5 times 1 plus 3. Right? So that would be 1 over 2 times 5 plus 3, which is half times 8, and that is 4. It works. Works for the first guy. Right? Now for me, for some done for peace, I like to do that for 3, at least 2 more. So n equal to 2, left hand side, right hand side. And this is because this is sum. That's why we're adding it. If it is not sum, you don't add it. So we shall come to those later on. Okay, if it is not sum, this is because it's sum, so we have to add the first two. 4 plus 2, 4 plus 9 in this case. Sometimes they'll say this and this, you use n equal to 2. But in this particular case, n equal to 1 means the first guy, n equal to 2 means the first and second guy, and this is sum. If it was product, we'll multiply. So it depends on the kind of question. That is why this is still part 1. Let's start with the simple ones. So n equal to 2, 4 plus 9 is 13. Okay? Now in this case, we have here on the right hand side will be 2 over 2, then 5 times 2 plus 3. Okay? 2 over 2 gives us 1, then 10 plus 3, and that is 13. So it works, n equal to 2. Now n equal to 3, left hand side, we have 4 plus 9 plus 14. 13 plus 14 gives us 27. Okay? Right hand side, we have 3 over 2. Okay, this is the right hand side. This is the right hand side. 3 over 2 times 5 times 3 plus 3. So this will give us 3 over 2 times 15 plus 3, which is 3 over 2 times 18. Okay? 2 into 2 is 1, 2 into 18 is 9. So this is 3 times 9, and that is 27. So it works. Alright. Now, we now come to this is just for me. You don't need to write this. You don't. First step, initial step. Second step, induction hypothesis. Or you can say inductive hypothesis. We assume that this works for n equal to k. Assume n equal to k. So we write the whole thing, 4 plus 9 plus 14 plus ellipsis plus continues 5k minus 1. Anywhere we see n, we put k. Anywhere we see n in the formula, we substitute it with k. So 4 plus 9 plus 14 plus continues plus 5k minus 1 equal to k over 2 times 5k plus 3. That is induction hypothesis or inductive hypothesis. The third step is now induction step. Induction step. Okay, let n to be k plus 1. Remember, this one is assumed. Assume it works for n equal to k. But this one we now say let n to be k plus 1. We don't say assume n to be k plus 1. No. You say let n to be k plus 1. Alright, I start with my left hand side. So let me write this for k first. 4 plus 9 plus 14 plus, continue, plus 5k minus 1 plus 5 times k plus 1 minus 1. Okay? So you get the k and then add k plus 1. You get the k and then add k plus 1. So this is my left hand side. So as you can see here, I'm using a color, a chalk here. This right here is the k. And we are now adding another guy here, k plus 1. So before I continue with this, I want to first of all, excuse me, I want to first of all see what I will get on the right hand side. Okay, because that is the main thing. To proving that the left hand side will give me the right hand side. After all, we know it works anyway. We just have to show that it works. So I'm gonna come here. I'll come right here. And then on my right hand side is k over 2, 5k plus 3. Actually, my right hand side is this, n over 2. Okay, n over 2, then 5n plus 3. 5n plus 3. So I'll just say, let n to be k plus 1. So my right hand side, this will give me k plus 1 over 2 times, let me use a bracket here, times 5. Wherever I see n, I put k plus 1. 5 times k plus 1, close the parenthesis, then plus 3, and then close the bracket. So I will have k plus 1 over 2, then times, let me use this as parenthesis. I now have 5k plus 5 plus 3. If you distribute, okay, 5k plus 5 plus 3. So I have k plus 1 over 2 times 5k plus 8. This is what I need. This is what I need here. And don't waste your time trying to FOIL this. Trying to FOIL it. No. It is in factored form already. It is in factored form already. Don't waste your time trying to mess it up. Okay? Now, I will make sure that what I get on the left hand side will give me this. If not, we will not sleep tonight. We will continue solving until we get it. Otherwise, we will not sleep. Right? Okay. So this here is this. Okay? This here is this already. So this will be k over 2 times 5k plus 3. Then plus, this is sum, plus, you distribute this. This is 5k plus 5 minus 1. Okay? Now let's finish this here. Let's finish it here. So my left hand side, so I now have k over 2 times 5k plus 3, then plus 5k, this is plus 3, then plus 5k plus 4, because 5 minus 1 gives us 4. 5k plus 4. Alright. So this will give me, let me distribute this. I have to get this, folks. I really have to. I have to get this. I have to get it. I have to get this. So this gives me 5k squared plus 3k all over 2. Okay? Plus 5k plus 4 all over 1. Here, actually, you can also simplify this more by writing 1 over 2 times k plus 1 times 5k plus 8. You can, if we just get out a fraction, you can use this. 1 over 2 times k plus 1 times 5k plus 8. Alright, folks, let's do this fraction. Okay, let's do this fraction. let's actually finish, we can finish it here. So this, the LCD is 2. Okay, LCD is 2. This is already 5k squared plus 3k. And here, and I don't know how you like solving your fractions. I think some people will prefer vertical method. So let me just do the vertical method. 5k squared plus 3k over 2, then plus 5k plus 4 over 1. LCD is 2. What will you do to 2 to give you 2? You multiply by 1. So you multiply by 1. Whatever you do to the denominator, you do to the numerator. So this is just 5k squared plus 3k. No problem. Here, what will you do to 1 to give you 2? You multiply by 2. And whatever you do to the denominator, you have to do to the numerator. Okay, you have to do to the numerator. Alright? So this will give us 2 times 5k plus 4. Please, don't come and write without putting it in parentheses. This is an entity. So that is what some students do. They just say maybe 10k plus 4. Or they might say 5k plus 8. No, don't do that, please. This is an entity. So you do it distributive properly. And these are plus. Okay, this is still a plus. So now we have, let's get everybody all over 2. Because they have a common denominator now. So this is 5k squared plus 3k plus 2 times 5k plus 4. And this gives us what? 5k squared plus 3k plus 10k plus 8 all over 2. Right? You see that? I'm just doing it step by step. So we come back here to finish it up. And we now have, we can just say, let's make that 1 over 2, and then we can deal with the rest. So we have 5k squared plus 13k plus 8. Okay? 5k squared plus 13k plus 8. Now let's factor this. Let's factor this. 5k squared plus 13k plus 8. 8 times 5k squared, 40k squared. 1 and 40 will not work. -1, -40 will not work. 2 and 20 will not work. -2, well, negatives is out of the question because this is plus. Okay, so let's forget about negative. 2 and 20 will not work. 3, no. 4 and 10. 4 and 10 will not work. 5 and 8. 5 and 8 will work. So this is 5k squared plus 5k plus 8k plus 8. So this is now 5k. We factor by grouping. 5k, we have k plus 1 plus 8, k plus 1. So this will now give us k plus 1 and then 5k plus 8. Because we factor by GCF here. If you do not understand what I did here, please view the videos I did on factoring under algebra. Okay, under algebra. So we now have 1 over 2 times k plus 1 times 5k plus 8. And that's our right hand side. Our left hand side equals our right hand side. That means we've proved it. Okay? Alright? Okay, let's do another one. Question 3. We have here prove that if, prove, this one is a little bit, you know, we are coming from the small ones to challenging ones, right? Prove that if C1, C subscript 1, subscript, okay, C subscript 1, C subscript 2, up to C subscript N, and D are any n plus 1 sets, then parentheses union I equal to 1 up to n C subscript I intersect D will give us union I equal to 1 up to n parentheses C subscript I intersect D. Alright, this is the proof here. Proof by mathematical induction. Please, I don't want this to scare you. I know that these are not numbers. And like I said, by the time we do several problems, you know, you will understand this. We are going to still apply the steps that we used in the previous two questions, okay? We will do the basis, the initial step or basis step. I call it initial step. That's my preference. Then, I usually like doing it for the next two, but in this case, we're not dealing with numbers. We're not. So, I might skip that part for me. But we'll do the initial step, we will do the induction hypothesis, and then induction step. This here, you see that just is the parenthesis. If you look at this, this is the left hand side, this is the right hand side. On the left hand side, you see the parenthesis here, then intersect D will still give you the union of I equal to 1 up to n, and this here. You know, if you notice the difference. Okay, now, first step, initial step. Initial step. N equal to 1. Our n equal to 1. So, for n equal to 1, our I, because n equal to 1 means, because this means from I equal to 1 up to n. Okay, up to n. So for n equal to 1 means I equal to 1. That is what it means. Okay, that's what it means. So on the left hand side, you could just say C1 because we're just dealing with C1, C subscript 1 intersect D, and on the right hand side will still give us C subscript 1 intersect D. Okay? Because our n equal to 1 actually means from I, because this means from I equal to 1, the first guy. So we just substitute I to be 1. That is the initial step. The next one will be our induction step. Induction hypothesis. Induction hypothesis. So in this case, we say n equal to k. Assume for n equal to k. N equal to k. Okay? So we just write the whole thing, but wherever we see n, we put k. Okay? So we have parentheses I equal to 1 union I equal to 1 up to k. C of I, close the parentheses, intersect D will give us union I equal to 1 up to k, C of I intersect D. That is induction hypothesis. Alright. The next one will be induction step. Induction step. Let n to be k plus 1. So I'm going to start from the left hand side. I'm going to start from the left hand side in this case, as we've been doing. So we have I equal to 1 union I equal to 1 up to k plus 1. Okay, C of I intersect D. So this actually means, from what we've been doing in the two previous examples, you see we have up to k first. Then we now add k plus 1. That is what we've been doing. We get all of the way up to k, then we add k plus 1. So this is actually union I equal to 1 up to k C of I. Okay? Intersect D, then union, so let's put this in parentheses, union C of k plus 1. You know what, we have to put union of C plus k plus 1, then intersect D. So let's put this in bracket here. This is the k up to k first, then union, the next one, C subscript k plus 1. We now close this here, then intersect D. Intersect D. Because this here means this. We get it up to k, then add k plus 1, intersecting. Okay, before we continue, let's see what we need to get on the right hand side. Okay, let's see what we need to get on the right hand side. So I'm going to, oh, this is I equal to 1. So my right hand side, this is what I need to get. Right hand side, I will need to get union I equal to 1 up to k C of I intersect D. Okay? Then union C of k plus 1 intersect D. Because this is in parentheses. This is in parentheses. So we treat it as such. So I can come here now. I can distribute this, distributive property. So I have my bracket. I have parentheses, union I equal to 1 up to k, C of I intersect D, close this. Okay, then union, parentheses, C of k plus 1, C subscript k plus 1. I should be saying subscript. Okay, not C of that. This is not a fog and golf. So C subscript I intersect D, close the bracket, union, parentheses, C subscript k plus 1 intersect D, if you use distributive property here. And this gives you right hand side. So you see, this gives you right hand side here. See that? And that is how you prove it. Okay, folks, we're going to stop here tonight. Okay, watch out for other videos. If you have any questions, please feel free to ask. Thank you so much for listening.
And you have a good